Hi there, this is MG5004 DE5418, whatever, and topic 3, and it's class 2, and I will actually do most of the work on partial fractions in a separate video. Just to start off with, though, with linear fractions, there are rules, there are ways you recognise how to break them up, how to decompose them, that's the correct word, that if you've just got, in the first case, 2, 3, 4, however many linear factors on the bottom, then you break it up as a number over each of the linear factors. If you've got repeated linear factors, then you break your original into a number over once times the linear factor plus another number over twice the linear factor, or squared, plus a number over the linear factor cubed, in as far as how many you need to go up to. So in this case there's 3, but if it was 4, you'd obviously go up to 4 fractions, and so on. If you're looking at a situation where you have a quadratic on the bottom, then you can break it up so that you've got the ax plus b over the quadratic plus c over the linear factor on the bottom. As I've said, I will do these in a separate video. So, separate video for these ones, and we'll look at that shortly. Before we move on to further work, let's just have a look at the idea of proportionality. Suppose we've got a statement y equals 3x, and it's obviously got two variables, y and x, and if you remember, x is the independent variable and y must be the dependent variable because y depends on x. So whatever you've chosen for x creates the y. So also we could think of that y is a function of x, and in this case, if there's an increase, if an increase or a decrease in x leads to an increase or a decrease of the same proportion in y, then we talk about this as being directly proportional. So if we've got that one there, if y equals 3x, then y is directly proportional to x. There's a direct proportionality there. So we could write that y is proportional to x, or that y is equal to some number times x, where k is this coefficient of proportionality. Now, if we've got it the other way round, if an increase in the independent variable leads to a decrease of the same proportion in the dependent variable, then we have inverse proportionality. So then what you've got, if it's inversely proportional, so if y is inversely proportional, then we'd say that y was proportional to 1 over x, or that y was equal to k times 1 over x, or k over x. Now, a lot of these things are really important in engineering. Hooke's law, that's about strain being directly proportional to stress, so that we would say that strain was directly proportional to stress, or we could write that strain was equal to some constant times the stress. Charles's law says for a given mass of gas at a constant pressure, the volume is directly proportional to the temperature. So we would say that the volume is proportional to the temperature, it's directly proportional, or we could say that V was equal to some constant times the temperature. Ohm's law, similarly, I is proportional to V, and we could rewrite that as I is equal to some constant. And the same with Boyles law. We could write that as the pressure because we know that V is inversely proportional to pressure, so that we could say that V was equal to some constant over the pressure, which if we rearrange it as PV equals some constant. From the previous slide where we looked at Hooke's law and saw that the stress was directly proportional to the strain, then we get that is true, or that we could find that K was equal to sigma over E, so that the stress is sigma and the strain is the funny E. So we could work out K. We could work that that's going to be equal to 25 times 10 to the power of 6 over 0. Let's make sure we get 1, 2, 3 zeros. So K is equal to 200 times 10 to the power of 9 pascals. And those of you that need to know, or do know then, that K is Young's modulus of elasticity in this case. Now we could do a similar calculation for B when we've got that is true, or we could rearrange that. And you're told this time that the stress is 18 times 10 to the power of 6, so that we could use the previous value of K and find that the strain is equal to 18 times 10 to the power of 6 over 200 times 10 to the power of 9. I just realised that the page references you see here I think are to a previous edition of your textbook, but it's around 273, and you can figure out that you're in chapter 7 anyway. Okay, so we know from Boyle's law that V is equal to some constant over the pressure, or that the constant is equal to P times V. In this case, P is 200 times 10 to the 3, and the V is 1.5 cubic meters. So K is going to be 200 times 10 to the power of 3 times 1.5, which is 300 times 10 to the power of 3 if you've put it in engineering notation. For part B, if we now want to find the volume, so this is part B, so the volume is K over P. We know what K is now, so that's 300 times 10 to the power of 3 divided by the pressure that we've been given. So that's not quite right. The pressure is 800 there. So 300 over 800 would give us 0.375. And don't forget you've got a unit which would be cubic meters. You're asked then for part C to find the pressure when the volume is 1.25 cubic meters. So 1.25 is going to be equal to 300, the constant, times 10 to the power of 3 over the pressure that we currently don't know. And if we just rearrange that, P, the pressure is going to be 300 times 10 to the power of 3 over 1.25. And use your calculators or your brains. And that'll be in pascals.